going on, Basement Hackers? Today we're going to get back into the linker scripts for GCC ARM. And last time we did the beginning of this one tutorial. I'll bring it up again and kind of do a quick recap of what we learned. And we have our linker that we're trying to do. At some point we got to look at the machine for the quick emulator and see if we can get the machine to we need to make our linker script match up the memory layout to the machine for the TI chip. I did buy the launchpad. I said I was going to do that, so you don't have to worry. I got that in the mail. I actually bought two, and I'll bring that up so that everyone can see that. Yeah, let me bring up the coding and we can just get into it. So if we go into, here is the launchpad I got for this chip. I know it's not the exact chip that we had, so the chip that the emulator supports is really this one, the 6965, but as it shows here, not recommended for designs anymore. So their emulator for quick emulator really doesn't is meant for this, and there's one other chip that it supports, but they don't really make this anymore. And then they suggested these. I went down the road of IoT because that's kind of what I do, and so I thought it was a good idea to go that path. So I went to this one, then found the launchpad for it. So you'll notice the 1294 is the 1294. So we got the launch pad for the IoT one that was recommended based on this chip, and we should be able to, hopefully they're similar enough. I'm pretty sure this is actually a Cortex-M4, which is actually what I wanted to do from the beginning anyway. We know the emulators are Cortex-M3, but that those are really close to each other. The only thing that really changes is the floating point and some of the math and the precision and speed of it, stuff like that. So let's get into it. We'll come back to this, probably break it down, learn about it, download the manuals and stuff, maybe look at the getting started guide just to get ready, so when we have it we know what to expect. I think I've even seen this board before. I think we have some samples of it. It has a lot of I/O. Looks like it has like Ethernet, USB. We'll get into that later though. So let me take this off screen. So getting back to the tutorial, let's go top down, bring us to the top, and then we can come back down and see where we were at. My screen's blinking. Still didn't get a graphics card yet. I'm hoping to save up to get a good one. So yeah, let's go top down. So we know linker scripts. They have input files, output files. You can supply your own script. You can use the pre-built, the ones that come with GCC. We kind of dove into the tool chain and found some of them. We're not sure if those are the exact right ones, but there was ones for different versions like V7, V7E, things like that. And then we looked at some of the compile options and how we saw that you can actually get like partially linked things. And maybe at some point we'll go into that more. Then they kind of broke down the terminology here. So we knew that there was virtual memory addresses and there's actually the load memory addresses, and we still have to kind of understand use cases for that, but it was something to do when you're loading stuff from ROM and how that's going to make your virtual memory addresses different than your load memory addresses, but in most cases they're going to be the same. We know that there's loadable, a section can be loadable or allocatable, and there's input sections from the input object files to the output sections to the output file, which would be our ELF file or executable or whatever our output is going to be, which is normally our executable or binary. The input files are usually object files or archives of our object files. And what other things? There was section contents, which has the data in it. Object files has symbols that are in symbol tables. We saw that there was object dump and NM, and how you can take an object file and you can kind of introspect it and see what's inside it and see the symbols. coming down, we saw linker scripts are just files. Let me mute that one tab because I'm hearing it chime. It said, for some reason it says it's muted, but it's not actually muted. So it definitely just heard it. Okay, you can use C-style block comments. They're just text files. Coming down, here's like their first hello world of one, where they're showing, so just the recap. So every linker script has to have sections, I'm pretty sure that they said. It's like the one requirement. We know that this is the line counter. No, it's the logic counter. What is it? Location counter? Where is it? I know they say it somewhere here. I think it's the location counter. Kind of like the PC, like a program counter. It's like how you're advancing through it. Where is it? Oh, location counter, yeah. So the period is the location counter. So they're advancing it to this address. So they're doing an assignment. This is a assignment expression. So they're moving the location counter. Then they're saying load from all of the input files. Get the .text sections out of them, and you're going to put that into the .text section of the output file. And since this is where their current location counter is, that's where this is going to be loaded in, where the .text section is going to be. Then it says to assign, this is assignment, what do they call it? Assign expression? Where is it? It's somewhere around here. The screen's blinking again. Yeah, simple assignments. Yeah, it's just an assignment. So you're assigning to the location counter symbol this address. So it's like 8 million hex. And then they're going to put all the data sections from all the input files into .data. And then they're going to get all the BSS sections from all the input files. That's what the star wildcard is. And put them into the .bss section. Let me make sure that everything is up and running actually properly. Is audio going good? Let me just check that because I've had it bite me before. All the data. Yep, it is. All right, great. So, going through this more, let's see. They break down that file and kind of describe that. You can have entry point. There's a cascading ways to define the entry point and override it. So from the command line, we'll always override anything in the file. Then you can have your entry point command. I guess it's a command. Yeah, it's a command. Entry. Yeah, script command. Okay. Then if you don't have that, it'll always fall back to start, which was interesting to me because it's not like main. Like start is actually a linker keyword or symbol that matters. Then and then it starts getting fancy and it's just like, well, we'll just try the text section. And if you don't do that, then we'll just go to 0. So that's the worst case scenario. It'll go to 0. And if you don't put anything at 0, it'll just no op all the way until it finds something and runs. If a 0 is a no op, or if memory's blanked out and stuff. Then we looked at other different types of commands. You can include other linker scripts, so you can kind of organize your program like how you want. You can specify a whole bunch of input files. So this is if instead of feeding them into the linker with the linker script, you can have the linker script itself reference object files. This would be important if you kind of wanted to bundle up an SDK and you were just like, well, here's my startup.object, startup being a very special one that's going to be packaged in, and you don't want to have the ingester of the SDK understand what all that is and understand that they need to feed that into the linker. So it's just all done for them, and then they're just caring about the things they're compiling and what they need to be linked at the end. Group, what was that about? Group was the same thing, but it kind of made it go after, I think. Oh no, it was for archive files, and you could do input on archive files, but you had to have the -L on it. So this just makes it so you don't have to do that. I think it should be L. and capital L tells you where to go look for those, and then the little L like that, and then it puts the lib on the front of it and all that good stuff. Then output is a default output file name. Instead of being a.o, a.out, you can specify one. Now, most of the time, a user is going to use the -o and specify the file name so that they're controlling what the name is. But if, say, you didn't want to, say the user doesn't do that, you can at least default to something, and it looks like a little bit cleaner and better. So that's just, I mean, it makes sense they're going to have a command for it. Search directory, I think this is like, yeah, it's like the -L, so the linker script can add where to go look for files. I see that less like valuable, unless maybe you're a DevOps person and you're trying to make all of them, all of your projects somehow include like a common like set of object files and stuff that you're controlling throughout your organization. Not as much for an SDK, but for more just like in general, if you're controlling the file system of the dev machines and the build machines. Let me just answer one thing for work. Sorry about that. It's just I was running something important and I just need to tell them that I'm done with it. Sorry. Alright, I let them know that they're good to go. Let me put this here. Does everything look good on the screen? Yeah, alright. Actually, should put the backlight on. At some point soon, I'm going to get my actual lighting, and then it won't look all washed out, and we'll try to fix some of that. But startup, what was that for? I think that makes it come before all the input ones. Startup command is just like input, except the file name will become the first input. So if you're wildcarding, it comes before that. So if you have a bunch of inputs and you're like, well, I kind of need this first, it'll do that, I think. It will become the first input file to be linked, as though it were specified first on the command line. This may be useful when using a system in which the entry point is always the start of the first file. Yeah, that one I don't think as important, but I'm sure somebody has like a very specific use for that. Then there was output commands. You have to specify, what was the BFD? That was the binary format descriptor. I think it was binary format. I don't think they said it anywhere here. So, was that it? Binary? No. BFD. What's it called? Object file. It's binary file descriptor. Yeah. So it's going to tell you the format. So if you had like, there's a MIPS ones, or you might even be telling it your output file is going to be like an iHex for Intel hex, or a binary format, or there's probably a whole lot of them that you can specify. And I think they tell you a command that you can see all of them using object dump. There's a command somewhere around here. Maybe it might have been further down. Usually they tell you like. And then this one lets you tell you what's the default. If they don't say it's in little or big endian, you can say what the default is. And then for big, if they say I want it in big endian, then you can specify what your output format is. So like you can even just say no, it always has to be in big endian, even if somebody says to make it in little endian. And this is like normal GCC flags that you'd pass for that. But what was? I could have sworn there was a command line. Maybe it was in here. This is how you could specify it on the command line to say what was it again? Binary file descriptor? Binary format descriptor? I know it's probably staring me in the face, but I don't see it. Maybe it was in here. Here's the linker output. Well, anyway, there is some flag that you can go see and dump out all the object dump to see what formats are supported by the whatever instance you have. Continuing down, We saw that you can do assertions, and you can assert on something. So one of the examples we looked at that came with the GCC example projects. Let me see if I have that up. I'm on my Vagrant machine. I can show you that really quick. Actually, I think I left off where we kind of were. And yeah, right here. They have an assertion right here that looks at the stack doesn't overrun the heap because your RAM is. So this would be at compile time or at link time that it would assert this, and it's because your program's too big and it pushed all of that on top of each other, and you have a stack size and a heap size that is defined somewhere else, but because your program's too big, you don't have enough space left over for it, so you can't actually load your program into memory. Okay, so coming back down, so that assertions are great. Like you want to have compile time failures instead of runtime failures. Extern. This is, I think, when it's kind of like extern in C. You're going to define that symbol later, or you're going to link that symbol later. So you're going to say, don't worry about this being unlinked. And so if you're making archives or partial linking, then that's when you would do that. Force common allocation. What was that for? This command has the same effect as -D to make it common symbols. I forget exactly what that was. I don't want to go back through all of this. This is like your fallback for your output BFD that like they were specifying up here. And no cross references. I think that's if you have multiple of the same across archives or something of the same symbol. You can go back to the last one if you want to see it. Provide, we're going to learn soon, and that's one of the ones we really need to understand because we saw it a lot in their throughout. Oh no, keep was the one. Provide, we did actually learn last time, but I don't remember it, so maybe we'll read that today. What was provide? Well, let's go straight down. Here's all the different assignment expressions. So you can just, like we saw in the example up top, you can assign an address. All of the assignments or all the expressions need to end in semicolons. White space doesn't matter, like most programming. But yeah, it's all the normal operators. So an expression can be complicated. And let's tear this one down, and this will help us. So here they do an assignment outside the sections block, I guess you would say. I put my curly brace on. I don't do open format. I do closed. I might even have that backwards right now. But then, so they have an expression. They assigned a 0 to this symbol, and then in the sections they define a section, and the colon is important. Just like that's how they differentiate with the tokenizer the difference between an expression and a section. And in this section they define, what do they call that? I forget. But this is a block defining the expression, and they say grab all of the .text from all the input files, and then that'll do that, and then at the end of that they're going to make this new symbol with the current location counter, and they're going to put that symbol into _e text, so the end of the text section. Then they're doing something tricky here. They're taking the current location counter, they're adding 3, and then they're anding off the inversion of 4, so they're the last 4 bits. So they're actually byte aligning it, or word aligning it, I should say, to the next word. And so that's the beginning of data, is what the B stands for, B data. And then they start a data section. Excuse me. And then they put all the data from all the input files into the data section. And so that's pretty cool. So they showed off how you can do complicated expressions here to do math on the current location counter. Provide. So let me remember again what. Oh, provide just means like lazily do it. That if something else defined it, then use theirs. And it's because symbols mean something in in old ANSI C, but there might be other symbol, like the symbols actually might mean something in general, but they're like, oh, if eText is already defined, then just leave it, but it's like a lazy initialization of eText, which still doesn't. It seems like it would be wrong if someone else was putting it in, because they wouldn't know the address until. But anyway, in this example, if the program defined this, the linker would have multiple definitions because they're not using provide for this line. But then for eText, they're using provide, so then it would silently use the definition in the program. Okay. Sections command, they're kind of just talking about how they kind of just ignored that up to this point. Now they're like, well, this is one of the main key blocks, and they all are needed, and they're section commands. Each section's command may have be one of the following. Yeah, I think that's a typo. It could be an entry, a symbol assignment, which we saw right here. An output section descriptor, which is what all of these are. This is describing an output section, and an overlay description, which we haven't learned about overlays yet. And I'm hoping to see what that means in a little bit. I forgot what entries were. The entry point. I mean, it is the entry point, but I forget how that maps into stuff. It's the first instruction to be executed, but how does it know? How does that tell the hardware? I mean, the hardware is going to just going to, like, based on the hardware, like, it's going to either start at 0 or some specific address that's based on that architecture. And ARM, I think, is always 0. So I don't know how the entry point actually works. You can use the entry point linker script command to set the entry point. Yeah, I actually don't know how that actually works when you get down to the end binary. Why the entry is anything special? You think you would just put the function you want to be your entry point at the location that is the beginning of where program code is initialized at, like at the 0 address or whatnot. Let's go down. So yeah, you could put an entry outside or inside the sections command block, I guess. So now they're going to talk about individual section commands, and then there's like, you can have an address, and this will give, I think, the virtual memory address. Virtual memory address, which is what they did here. And we saw from the example that we were copying off of that was for the quick emulator, they had that. And what that does is if there was a load address or alignment matters. So yeah, they talk about alignment here. But when you know that the current program counter is at the exact address you want it at, you could say, no, put it at this address. And so we're filling in this address right here. We didn't see type yet being used, or a lot of these other ones. We saw from their examples that came with GCC that they described regions. Like you see that they're saying flat, like put it into the flash region, and that actually goes back to their memory layout. So it looks like RAM and flash are the two regions, but we haven't really learned about how that works yet either. Yeah, so like here they're saying map it, this output section to what do they call it? That region, to the RAM region. Most output sections do not use most of the options. Yeah. And we didn't really learn about some of these other ones. I think we saw some fill expressions, but output section names, they talk about how these are the three main ones, but based on your BFD binary format descriptor, you're kind of going to learn what output sections you have. So if you go to here, they have data, BSS, they have a heap defined, a stack dummy. There's a whole bunch of output sections. Like some of these are ARM specific, .text, like .text is a common one. What was some of the other ones? If you have a 0 table, and this is if you're having two different BSSs, which BSSs were they were loadable but not executable, I think is what we were saying. That they are allocatable but not loadable, because you're not loading anything into them. They're just blank data that you can allocate out of as you go. So like variables will be there, but the heap would be that. In most cases, this memory must be zeroed out. So you might use that assignment expression to do that. Let's come back down, or that fill expression. So they talk about the difference of this and this, where the period is here for that virtual memory address. I think it's the virtual. This address is virtual, but I'm not 100% sure. Yeah, it's virtual memory address, not the load memory address. And then they do stuff like, you can make the virtual one align, and on this is a 16-bit alignment. Or is that 16-byte alignment? I guess it would be byte. Yeah, you wouldn't be bit addressable, right? 16-byte, yeah. If you wanted to like specify that to align on something. So we haven't caught up yet, so we're trying to just get back to where we left off. Then they talk about how the input sections, how you can access them with a wildcard, and you can say all the input files, get the .text. This will do all the input files with .text and the .rdata sections, and how these are similar but different. They're similar in that they'll get all the input files and get all the .text and .rdata, but you'll see .text, .rdata, .text, .rdata as they go through each file, where the next one would be, if you were going to assign to an output group, you might do all the text data, text input sections, and then all the rdatas for that one output section. So it's a little different. Or you can even call out specifically this object file, I want this input section from it for my output section. Then they talk about wildcarding. You can match on characters. It can get elaborate, so you can do. They'll show like, you can be like any of the input files that have capital letters then as the first letter, or all caps. I guess that would be. Get the data section and put it in the cap data section, and you can wildcard inside of here too. So you can do like get all the text sections that end with anything, instead of having to explicitly call it out. So yeah, you could do character sets. There's always an escape character, so there's fun stuff. They also had some weird stuff like never put a slash or weird characters into your file names. Some of them just won't work. What was the one that just won't work at all? It just totally screws it all up. I think it was forward or backslash or something. I mean, who would do that in the first place? You can also sort. One thing that's interesting is you can't tell it to sort by a certain way. Like, you can't give your own. You could change this by using the sort keyword, which appears. I think they showed a sort in one of these. But anyway, yeah. So here's an output section that has all the input files, .bss's, followed by all the input files common sections. And common was a weird one. It's like some of the binary format descriptors, some of the types of object files will have these weird common sections, and then some of them are even weirder and have .s common sections, and it sounds like something that's very specific to certain formats, and I would figure that out when I need it. Keep was something that we were about to learn, I think, and I think this might be where we left off. I think we're there. Yeah, we're about halfway. So let's read this and try to mess with some of these. So it looks like this has to do with C++ though, which would make sense why they would be using it in these, because this linker script is from GCC ARM, which could be doing C or C++. So keep maybe is something I don't need. Let's see. So input section and garbage collection. When link time garbage collection is in use with GC sections is often useful to mark sections that should not be eliminated. This is accomplished by surrounding an input section's wildcard entry with keep, as in keep all the input files .init, or keep with a sort of all the input files .ctors or constructors. So where are they using it? So keep the interrupt service routines, keep the .inits, the .finit. What is finit? Let me think. Final init? What is it? What is it? What does it stand for? It's probably like the opposite of init. Nope. What could it be? Executing init and F and I and I. This is what we're just in, but why? No. You think this would be easier? Well, we know it goes with init. I wonder if we can see like input, linker input sections. Say I-hats. Really? I don't know why this is so hard. Alright. Well, anyway. Maybe not how I got on that tangent. Let's keep going. The following, so, because I was reading it in here. So we'll figure out all the different possible sections. But constructor, so you can see things like how they're wildcarding, and they're like getting all the files, the input files that have CRT, which would be the constructors beginning. So anything that ends with CRT begin.o, or that has it in the middle with at least one character after, and then they exclude certain ones. Yeah, it's like crazy. Then they sort certain stuff, and all of this is going to go in the text section, but they're kind of organizing it top to bottom. Then there's destructors. Then ex tab, And see how they're making expressions where they're saving where things are, because then they might use those. So I mean, these are commented out, but if you want to put them in, then you're going to have this symbol here to be able to put and into this spot in memory. So this table will have, they'll align on it, and then they'll put all the addresses in the specific spot in memory. So it's like where the BSS starts and ends. Or I guess start and length, because they're taking the end minus start, and then the second one's start and the length, and that's the table. And then they could see where the beginning and the end of the table is for the 0 table, and the same thing for the copy table. So yeah, really cool stuff. We can read most of this now, but there's still like a lot to understand. Like, so provide with underscore hidden. It's almost like the provide. We just learned. Reminded that that was like a lazy loading version of defining this guy, but I don't know what hidden is at the end of it, so that's interesting. We haven't learned keep yet. Okay, so back to it. The following example is a complete linker script. It tells the linker to read all of the sections from the file all.o. Oh yeah, because you don't have to put what input sections. You can just specify the whole file, so it won't even it'll just get every single section out of it and put it into this output section at this address, and then it'll take this input section from this file and put it following that in this section. But okay, all.o, and place them at the start of the output A, which starts at location 10,000 hex. All of the sections .input 1 from foo.o, and I'll read the next one and then come back up here. So output.b is going to be the foo.o. This section out of it is going to be the beginning of output B, and we know that since the location counter hasn't been updated, it should just immediately follow this, but it will be aligned to the next boundary based on, and we know that that is based on the worst case scenario of the input files. It'll figure that out and go to the next boundary. Then it'll go to this file and get this input section out of it. That'll go in there. Then it'll go to the next boundary for output C, and then it'll get all of the files that are left. So like this one's already been eaten up because you can only have an input section once. We learned that from one of the sections above. Which section was that? Because we actually didn't kind of pay attention to that. Because we learned that. Oh, here. They said this would be an error. Probably is an error because they already ate up every single data section, and then they're like now calling out a specific input file for the data section, and they're like, that would be bad. And then they said somewhere else, they're like, well, you could have a scenario, I forget exactly, but they're like, oh, and then there's a scenario where you're going to eat up the startup script. Oh, actually ours does that. Ours will get the text section out of startup.o, so calling out a specific object file, put that into that output section, and then they're going to get the text sections of all of the rest of the input files. That was what it is. And that was based off the example we got from the guy that did the quick emulator example for, I forget what it was, the versatile PB emulator machine, and you can go back to my last videos to look at that. So coming back here, so they're going to get the rest of the input ones and the rest of the input twos, put them in C, so all the ones are going to come, and then all the twos for anything that left that's passed in, and that's going to go to output C. I did notice there's no period there. I guess the sections don't have to have a dot at the beginning, but it's common for them to. But like all these have it for the input sections, but these don't for the output sections. But okay, now let's read the rest of this. All of the sections, the .input 1 from the file foo.o follows immediately in the same output section. All of the sections .input 2 from all of section .input 2 from foo.o goes into output section output B, followed by section .input 1 from foo.o or obj or whatever you want your extension is. All of the remaining .input1 and .input2 sections from all the files are written to the output section output C. Cool. Sounds like a plan. One thing I did want to go back and just kind of confirm myself on that alignment thing, because that's a technical detail that is important, but I didn't know exactly, and I feel like most people are gonna like skim by that and never really understand it fully. Where was that alignment thing? It was when they were talking about how to specify that virtual address, right here, and they're saying the second will set it to the current value of the location counter aligned to the strictest alignment of the .text input section. So the strictest alignment of the input section, not the output. So of all of the input sections, or is it of the input section that you're bringing in? That's still, I would probably need, because I don't know how that works when you have a lot of object files, and they can have different alignments. We know that each input file can have different alignments, and there was a way to actually specify what your alignment would be, so with a line, and ignore the input files. But I don't know how that works when, I mean, it's the strictest, but what if there's other sections? Is it the strictest across all of them, or is it the strictest to get across all the text that are in this one? What if there's a second group in this block? Like that's a little weird, and there's probably a little detail there that's hard to figure out, and you'd have to go kind of dive into the man page. But most of the time you're going to be explicit about all this, and it won't matter. But if you're trying to like find a bug, it might be something you have to figure out. All right, coming back down. Actually, I think we did read a little bit about these. Did we jump around? Did we get past this? No. Did we? Yeah, I almost think we got past this, but I don't remember some of what we're reading right now. Because I remember these expressions, but let's just keep going. You can include explicit bytes, and we saw this in right here. We saw when they were building that table, they had these longs here, and so you could put explicit bytes of data in an output section by using byte, short, long, quad, or squad as an output section command. Each keyword is followed by an expression in parentheses, providing the value of store. The value of the expression is stored at the current location of the location counter. Yeah, so back in here with this table, they update the location counter, but they align it. They just do an expression to save where the location counter is now. Then they say, all right, well, take one of our variables up top for the beginning of the BSX, or the start of the BSS section, the output section, and then do some math here and compute the length of it. And so now you have to start in the length in a table, and then the next long will be the start and the length, and the next long after that will be the length. So now you have 4 longs, and it's the start, length, and now somebody can go to this address, because this is the beginning of this table, and go and walk through it until they get to this address, the end of it, and know where all the BSSs are. And if you wanted a third or a fourth, you could just add it in, and all you just need is these variables, and or symbols. And we can go find this symbol right up top. So underscore BSS. Here's start and end right here. So it's the start, they align, and then they say, oh, here's the start of it, and then they dump all the BSSs in it, then they dump the commons, and then here's the end. And so then they can compute the size and everything. They could have even just computed the size here and not done it when they're doing the long, but whatever. they only need that table. You have to uncomment this out, and that's only if you wanted to have two different BSS sections. Same thing with this copy table, so that they can have two different data sections as well, which we know the data sections is data that's going to be copied in and initialized, where the BSS is just allocated and then used at runtime. So like any non-initialized static or global variables would be in the BSS, where the data would have initialized values. That's why in embedded you would probably most of the time to save the size, you actually don't want to initialize things that you know you're going to zero out anyway, or that you don't care, that because it will actually eat up some extra space. So going back to this, okay. So the value is stored, and the value is always going to be some math you're computing based on sizes, lengths, addresses. So it's always going to be like a number that has to do with an address or a size of something. The byte, short, long, and quad commands store one. I thought there was squad also. They decided not to mention it the second time. 1, 2, 4, and 8 bytes respectively. And squad would be 16, I'm assuming. But I actually don't know what... I've never heard squad before. And yeah, I'm going to get squads from Call of Duty. Or whatever game they're calling out. Oh no, that literally is a game called Squad. Squad, linker, let's use GCC squad. What is a squad? Squad. What size is squad? Oh, it's a signed quad. Sign extends the value. Okay. I guess I should have kind of saw that, but I guess you're not really getting a lot of negative things though. So it's like most things are positive. So, all right, let's go back. Back here. So let's see. So sign extended quad. So that'd be also a 8-byte value like quad. After storing the bytes, the location counter is incremented by the number of bytes stored. Yeah, that makes sense. You're going to put a long in, now the location counter is after that. For example, this will store byte 1 followed by 4 bytes values for the symbol ADDR. So they put the 1 byte in with the value 1, and then they put 4 bytes in with the value of the symbol that of whatever ADDR has as its value. When using a 64-bit host or target, quad and squad are the same. They both store an 8-byte or 64-bit value. When both host and target are 32 bits, an expression is computed as 32 bits. Okay. In this case, quad stores a 32-bit 0 extended to 64 bits. And squad stores a 32-bit sign extended to 64 bits. If the object file format of the output file has an explicit endianness, which is the normal case, the value will be stored in that endianness. That makes sense. When the object file format does not have an explicit endianness, as is true for example, S records. Don't have familiar with that. Sounds like almost S37s, or 47s, or 37s, whatever it is. The value would be stored in the endianness of the file output or input object file. You may use the fill command to set the fill pattern for the current section. So a lot of times you're going to fill it with zeros, but I guess you don't. I don't know if you have to. It would be based on the hardware, or I'm not sure if you can make the BSS fill it. But it is followed by an expression in parentheses. Any otherwise unspecified regions of memory within the section, for example, gaps left due to the required alignment of input sections, are filled with 2 least significant bytes of the expression, repeated as necessary. fill statement covers memory locations after the point at which it occurs in the section definition by including more than one fill statement. You can have different fill patterns in different parts of an output section. This example shows how to fill unspecified regions of memory with the value 9090 in hex. The fill command is similar to the equals fill expression. We saw that as an option for a section command. Where was that? The optional fill expression. The fill command is similar to that output section attribute, but it only affects the part of the section following the fill command rather than the entire section. If both are used, the fill command takes precedence. So if you use this, it'll fill in between sections. If for some reason within a section there's gaps because of alignment, the assignment will do it. But if you use fill, it says it only affects the parts that follow the fill. I gotta see some examples. I wonder if there's any in here. Nope, fill is not in here. I wish they would have shown let's see if there's an example here. They're not using the fill command here though. They're using the fill I guess argument to a section output expression, an output section expression. I feel like this is when you want to like initialize it to like zeros or all F's or something like that, where you would want to use fill when you literally want to it's not just like just putting it to something. You're literally trying to say, I want to fill this with specific stuff. Yeah, some of these we'll need examples for. Pretty tired. What time is it? Alright. Output section keywords. There are a couple of keywords which can appear as output section commands. Create object symbols. The command tells the linker to create a symbol for each input file. The name of each symbol will be the name of the corresponding input file. The section of each symbol will be the output section in which the create object symbols command appears. This is conventional for the a.out object file format. It is not normally used for any other object file format. Let's see. The command tells the linker to create a symbol for each input file. Okay. So you're going to have a linker variable for each one. The name of each symbol will be the name of the corresponding input file. Okay, so you're going to have every input file is going to have a symbol based on the name. The section of each symbol will be the output section in which the create object symbols command appears. The section of each symbol. That doesn't even make sense. Of each symbol will be the output section. Oh. Wait, the section of each symbol will be the output section in which that command appears. This is convenient for a.out object file. It is not normally used for any other object file format. Is it a way to just kind of save all of the input file names into your output file? The section of each symbol will be the output section in which the symbol's commands appears. That sentence just doesn't make sense. Is this saying the input sections for each input file that has a symbol will be the output section in which constructors? When linking using the a.out object file format, the linker uses an unusual set construct to support C++ global constructors and destructors. When linking object file formats which do not support arbitrary sections such as ECOFF and XCOFF, the linker will automatically recognize C++ global constructors and destructors by name. For these object file formats, the constructors command tells the linker to create constructor information in the output section from the constructors command where the constructors command appears. I knew the C++ stuff's going to be really complicated. I kind of want to just come back to it because C++ is going to have a lot more sections, and I just don't know all the C destructors and constructors. I mean, we see this block, and it's up in the text section. Well, it's not exactly the same. I could have sworn that they had. Well, anyway. Output section discarding. The linker will not create output section which do not have any contents. This is for convenience when referring to input sections that may or may not be present in any of the input files. For example, if you do a .foo and you say get all the foo sections out of all the input files, we'll only create .foo section if the output file if there is a .foo section in at least one input file. So that's good. If you use anything other than an input section description as an output section command, such as a symbol assignment, then the output section will always be created. So that's a hack to make it, like, force it if you need to force an output section, even if there are no matching input sections. Yeah, so if you really have to force it to have an output section, even if it's empty, you can do that. The special output section name discard may be used to discard input sections. Any input sections that are assigned to an output section named discard are not included in the output file. So maybe if you wanted to purposely discard something and then wildcard get all the rest of the input sections and wildcard the rest of them, you could do that. It's kind of weird that you have to use the slashes in the output section name. Output section attributes. Wait, weren't we already past all this? Are they like repeating it? Because I know. Yeah, what is this? This is a description. Now they're going to talk about the attributes. Okay. Alright. We've already described the section, the address, and output section command. Oh, yeah. These commands. In this section, we'll describe the remaining section attributes. Cool. So we're going to learn about all of these guys. Output section type. Yeah, so we're going to go through the type, the load memory address. So that must be this guy here. So you can do the virtual and the load memory address. I guess it's kind of weird when they do stuff like that. If you're going to have a load memory address, you always have to have it in this. That's kind of weird. The type, the region, and all those. So we're going to have the type here, load memory address, the section region, the PHDR. It looks like you have multiple of them, and the fill. Output section type. Each output section may have a type. The type is a keyword in parentheses. Oh, that's what it meant. It literally says put it in parentheses. Because I was wondering why they had the parentheses there the other day. The following types are defined. You can have no load, which means it's allocated and not loaded, right? You can have desect. Sure. You can have copy, info, overlay. These type names, so the no load is the section should be marked as not loadable, so that it will not be loaded into memory when the program is run. Let's see what no load, if we have no loads in here. No load. And we're not going to have it in ours. What's an example of no load? Linker, no load. They're defining a ROM section that they're not going to load. They actually kind of do that. Why does it have like an extra argument? Because they have, this would be the name, this would be the virtual memory address, this is the load memory address. But how do they have this extra block here? It's not shown in here. Alright, anyway. These type names are supported for backwards compatibility and are rarely used. Okay, so I can ignore all these. They all have the same effect. Oh, okay, so you need to use one of them. The section should be marked as not allocatable so that no memory is allocated for the section when the program is run. Oh, so this is the name you should use. So it's not allocatable. Wait. They all have the same effect. The section should be marked as not allocatable so that no memory is allocated for the section when the program is run. That's not the same as this. So you have no load. So which one's the right one to use? The linker normally sets the attributes of an output section based on the input sections which map into it. You can override this by using the section type. For example, in this script example below, the ROM, we just saw that in another one. All right, so the ROM section is addressed as memory location 0 and does not need to be loaded when the program is run. The contents of the ROM section will appear in the linker output file as usual. I guess you can only have one of the two, but it still doesn't tell me which one I have to use. Is it overlay? I'm assuming it's overlay is what we should use. It's you either say overlay or no load. Output section LMA. Every section has a virtual memory address and a load memory address. The address expression, which may appear in the output section description, sets the VMA. The linker will normally set the LMA equal to the VMA. You can change this by using the @ keyword. The expression LMA that follows the @ keyword specifies the load address of the section. This feature is designed to make it easy to build a ROM image. For example, the following linker script creates 3 output sections. One called .text that starts at 100 hex, one called .m data, which is loaded at the end of the .text section, even though the VMA is at 2000 hex, and one called .bss, which hold uninitialized data at address 3000 hex. The symbol underscore data is defined with the value 2000 hex. Where's that? So the virtual memory address is this. They load all the text files, and then they have an expression that defines the end of text underscore e text. Then they have m data that has a virtual memory address of this, but they put it at the load memory address of the address of, I think they meant this. Oh, no, they're saying the address of this probably, and the size of that. So they're making it, so the load memory address is where you're loading it, but the virtual memory address is the address it's going to have in memory. And then they advance data to the load counter, or the location counter. Then they get, so they put data at, and then the end of data. So this is the start of data and end of data. They put all the data in it. Then they come here and they just put, this doesn't have an at, so the virtual and the load memory address would be the same probably. And they put all the stuff in it. This feature is designed to make it easy to build a ROM image. For example, the following linker script creates 3 output sections, one called .text, which starts at this address, and one called mdata. What's mdata? Which is loaded at the end of the text, even though it has a different virtual memory address, and one called BSS to hold uninitialized data at address that's not directly following it. It actually will be at 3000 hex. The symbol underscore data is defined with the value 200. Yeah, so which shows the location counter holds the virtual memory address value, not the load memory address value. That's interesting. So it's the virtual memory address. Okay. So most of the time you're talking about load memory address only when you wanted, when they differed will the LDMA, and usually it's when you're doing something like this. The runtime initialization code for use with a program generated with this linker script would include something like the following. The runtime initialization code for use with a program generated with the linker script would include something like the following. To copy the initialized data from the ROM image to its runtime address. Notice how this code takes advantage of the symbols defined in the linker script. Yeah, so you can, these symbols are accessible in code. So they extern those symbols. So they're going to reference eText underscore data, the end of data, bstart, and bend, which is the BSS start and end, or bend. So they extern all those. Then they say that the eText, which should be, this is where code should be, the beginning of your code should be. So they put that in the source, and then data, that was this guy, which should be the very end of eText, of the text section, I mean. And what they say, ROM has data at the end of text, copy it. So they go to the destination, and as long as that's less than the end of that, they're going to copy all that What? The source is at eText. Oh, the end of text. Yeah. Oh, yeah. They're going to load everything from there, from here to the destination, which is data. eText is the end of text. Is this an LMA? They just said. They're going to walk from here to here, starting at here, and just going as it goes, incrementing both of them, because they assume they're the same size. But what the heck? Right. The load memory address. This feature is designed to make it easy to build a ROM image. For example, the following linker script creates 3 output sections: a .text, which starts at 1000 hex, one called .mdata, which is loaded at the end of the text section, even though its virtual memory address is different, and one called BSS to hold uninitialized data at a different address. The symbol data _ data is defined with the value 2000 hex, which shows that the location counter holds the VMA value, not the LMA. I'm confused how these two aren't the same. Yes, the load memory address is set. So this is the virtual memory address of the end of text. This is the virtual memory address 2000. Which, oh. This doesn't have to be 2000. This one is going to be literally whatever it is. Oh, okay. Yeah, so say this went from 1000 hex to 1100 hex. There would be a gap. This would be 1100, where this would be 2000 hex, and we would start saying to copy from 2000 hex into 1100 hex all of the data until you get to the end of the M data. One thing that they don't look at is, what if they overrun? What if there's not enough room at the end of .text virtual memory address to support the size of this, of all of these? And then for zeroing the BSS, they just take the start and they go to the end. So destination, they assign the address of this, and then they advance it until it gets to this, and they just zero it out. So that makes sense for initializing. So this is going to move all of the static data on top, like in place. The other one's just going to zero it all out and fill it. Output section region. Like it's a little confusing, but I think I got it. Output section region. You can assign a section to a previous defined region of memory by using error region. See memory commands. So we gotta learn about the memory command still. We haven't looked at that. But it looks like you can just design. I mean, it looks pretty straightforward, and we've seen it on other places. But you'll do like flash. It's read writable or read executable. So you can. It has loadable code. I'm guessing that's what the X means. Say what the origin is. I wonder if this is a VMA or LMA. Let's say it is a VMA, and then this is the size. Same thing with RAM. Yeah, it's probably a VMA, and then size, and then you could say like load it in. So here's an example. They define a ROM, origin, size. They divide the sections for ROM. They load all the text into the ROM. Output section PHDR. I mean, that didn't really tell us enough, but hopefully they show us more examples. You can assign a section to a previously defined program segment by using PHDR. If a section is assigned to one or more sections, if a section is assigned to one or more segments, then all subsequent allocated sections will be assigned to those segments as well, unless you use an explicit modifier. You can use none to tell a linker to not put the section in any section at all. Looks like if you wanted to put like, they're like defining something special about this section, and then they're like putting that on that section. I don't know. Kind of losing focus. Where's the origin? I want to see if it's virtual or I think I'm actually going to call it a little early. I'm pretty tired. We got a little further. I want to get fresh on this. So Sunday I'll be back. I didn't even see if anyone was chatting. Oh, sorry. Section names vary depending on the compiler language. Good way to get rid of unit tests. So I'm gonna switch it up to just chatting. Oh wait, we wanted to explore a little bit this guy. See what stuff it has. We won't go too far into it, but maybe we'll download the manual at least. Description. this board Launchpad eval kit. Let me make it bigger. It's a low-cost development platform for the ARM Cortex-M3. What was the F? F meant like had extra math or something. Floating point? Yeah, I think it has floating point. Hardware accelerated floating point. I think is what F means, but I could be completely off on that. The connected Launchpad design highlights the MCU, and it has an on-chip 10100, so I think it's 10 megabits and 100 megabits per second. Ethernet, MAC, and PHY, and USB 2.0 hibernation module. I wonder if that's so you can really test like power consumption and stuff. Motion controlled PWMing, and a magnitude of simultaneous serial connectivity. So let's see the features. This is always the fun part. High performance, 120 megahertz, 32-bit ARM Cortex-M3 CPU, 1 megabyte of flash, 256K of SRAM, 6K byte of EEPROM. So that's for your data. Integrated MAC-PHY, data protection hardware. There's 8 32-bit timers. That's nice. I think that on the thing I'm doing, it got like 4. Dual 12-bit 2 MSPS. Millions of samples per second, I think. ADCs? I don't know. It's probably something like that. Motion controlled PWMs. USB, HD, and O. The many additional serial communication interfaces. Dual stackable booster pack XL connection sites. Yeah, so the rails here they're talking about. I think. It sounds right. You can click this. Cloud-based ExoSite quick start application, TivoWare 2.0. I don't know what any of that is. Onboard integrated circuit debug interface, multiple development tool chain support, CCS, Kyle or Keel, whichever one, IAR, Mentor, and GCC. So that's what we're doing. This is like the Code Composer Studio that TI uses, which is just an Eclipse wrapper. I think it's Eclipse wrapper. Almost yeah, it is. What's included? It comes with the eval kit, PCBA MCU, an Ethernet cable, USB cable for instructions, and so forth. It's only $20. Kind of why I went with it. They had like $200, $300 ones. I'm like, this has the chip on it and stuff. I mean, the other ones might have like some of the IOs and sensors already integrated on it, but I want to do all that myself for fun. So application notes, serial to Ethernet converter. So it sounds like you can probably screen into this or telnet into this. Oh, never mind. Serial to Ethernet. I was thinking serial to USB, like a FTDI. Serial to USB. Code Composer Studio, your development environment, Flash Programmer, GUI, and command line. We'll probably need this. What? I hate when they make you do that. It's so annoying. All right, I think that's good enough. Here's a standalone one. Why does it take me down there? Oh, that's cool. So there you go. Hopefully by Sunday maybe we'll have it. If not, it'll be on Tuesday's episode. Sunday we'll get through the rest of the linking. We should be able to easily do that. And then by next Tuesday we should have it linking for Quick Emulator and maybe the hardware as well. So till then, keep hacking in your basement, and it was fun today. Got an extra day in for like an hour or 2 hours. So see you then. Keep hacking. Bye.